Welcome back to the second portion of WaveMotion. We're working our way through different types of waves. We talked about the introduction, and now we're looking at barotropic instability. So barotropic instability deals with how long waves move. So here are some assumptions for long wave or barotropic instability. Our assumptions are that the atmosphere is barotropic. You remember we said that barotropic atmospheres means that there's no temperature gradient on a constant pressure chart. This is a hypothetical. When Rossby came up with this concept back in the 1940s, the late 1940s, they were still trying to get a handle on how to model the atmosphere. And this is one of the more simple more simple models. So it's hypothetical. What if the atmosphere was barotropic? What if there is no convergence or divergence in the atmosphere, just on big scales? No vertical motions, of course, if there's no convergence and divergence. No friction, because we're looking at the middle of the atmosphere. And another thing is that there's no shear vorticity. Those are a lot of what ifs, but how would the atmosphere respond if all of these were not important? So the one thing that really is important in a barotropic atmosphere is the conservation of absolute vorticity, meaning that as you're following a parcel of air, the absolute vorticity doesn't change. Now you could have changes between relative and Earth's vorticity, but following the parcel of air along, the absolute vorticity, the sum of the relative and the Earth's vorticity, is 0. So that means that if the Earth's vorticity increases, if F increases, then your relative vorticity, or zeta, decreases, and vice versa. So relative vorticity that decreases, let's see, if you have a decreasing relative vorticity, that means that your curvature must be less than 0. In other words, if zeta is negative, then your curvature is negative if we're assuming that there's no shear vorticity. And negative curvature means it's anticyclonic. So this is what you get. If for some reason the air is displaced, it's moving from the west to the east, and there's some sort of disturbance that makes it move to the north, then as it's moving to the north, the Earth's vorticity is increasing. Of course, the Earth's vorticity is a maximum at the North Pole. So as it moves north, it's increasing. So if absolute vorticity were conserved, that means relative vorticity must decrease, which means that you must have negative curvature, and you start to see a ridge. So this is for flow that's disturbed northwards. If flow is disturbed southwards, then Earth's vorticity would decrease, and to make that equation 0, that means that relative vorticity must increase to balance it, and increasing relative vorticity means it becomes more cyclonic. In other words, the curvature becomes more positive. And this is what it looks like. If the air for some reason is disturbed southward, then Earth's vorticity decreases and the flow starts to curve more cyclonically. So this is the basis for barotropic instability. Everything is based on the conservation of angular momentum. And barotropic instability is what's driving long waves. We also call them planetary waves. Another word that we use is Rossby waves. If you discover something, you can name it after yourself, and Rossby did that a lot. So really, this is what makes long waves. It's the It's the conservation of absolute vorticity. As a matter of fact, one more thing Rossby did was he looked at the change of vorticity moving, or Earth's vorticity moving Earth or north or south, in other words in the y direction, and he named a parameter after himself. As the Earth's vorticity changed as you moved north, that ratio was called the Rossby parameter, and we used the symbol, the Greek letter beta, to represent the Rossby parameter, how the Earth's vorticity changes as you move north or south. So in practical terms, usually you see wavelengths that are on the order of about 3,000 to 4,000 kilometers. These are your planetary, long, or Rossby waves. Here on the map that I'm showing you here, we've got about 6,000 kilometers from trough to trough. Now, we talked about wave numbers, and when looking at long waves, we like to count the number of waves that are in the hemisphere. In other words, all the troughs, count those, and we call that the zonal wave number. So simply look at the really big troughs and then count them. And in this case, on this map, I can see 5 really big troughs. Typically, you're going to see anywhere from 3 to 13 troughs or waves. Really not uncommon. But more commonly, you're going to see anywhere from 4 to 7. 3 to 13 is kind of the extremes, but on an average day, you're going to find anywhere from 4 to 7 around the northern hemisphere. And remember that these planetary waves are not really absolutely barotropic. They are equivalent barotropic, meaning that typically up in the upper atmosphere, the isotherms are parallel to the contours. As you get lower in the atmosphere, you start to see some temperature advection at 850 and places like that. But in the middle of the atmosphere, there's not a lot of temperature advection going on. So we can say that the atmosphere is equivalent barotropic. So I skipped all the derivations and I went straight for the equation. I bet you're proud of me. But this is the Rossby wave equation. And the Rossby wave equation, what it tells us how fast these planetary waves move. In other words, the phase speed of the waves. And we give the speed of the wave, we give it the letter C, we call it C. Now, the phase speed, or how fast these waves are moving, depend upon a few factors. One is how fast the wind is blowing, the average west to east wind. Also, it depends on the Rossby parameter, which is fixed for the most part. And then also, it depends upon the zonal wave number, the number of waves. So let's go through a couple of cases, a couple examples, trying to figure out the phase speed. So the phase speed tells us how fast these waves are moving, how fast they're moving through the northern hemisphere. And in terms of knots, you can actually calculate the knots that they should move using the Rossby wave equation. So here's a case, let's take a look at a case that will have fast moving waves. What would make that wave speed really fast? C would be fast. So of course it's pretty obvious that the faster the winds are in the atmosphere, the faster the waves move. At least that from the Rossby wave equation. So if U bar is big, then the waves are going to move really fast. Another thing that causes the waves to propagate quickly is the wave number. If you have a really big wave number, let's say you have 7 or 8 waves, really long waves, big waves in the atmosphere, then that makes that term on the right side, if you have a really big number, that's going to make that whole term small, and a small number subtracted from a big number still gives you a big number. So this is an important forecasting technique, is counting the waves. How many waves are there? The zonal wave number. If there are not a lot of waves, if the waves are just a few, maybe 3, then your K is small, which makes that term on the right side big. And if the winds aren't moving very fast, the average wind speed, U bar, then a small U bar minus a big right-hand side there, the beta divided by K squared, gives you a really small wave propagation speed. So the point I'm trying to make is that waves, planetary waves, will move slowly if the wind speed is rather slow. In other words, the average wind speed moving from the west to the east through these waves, the actual speed of the wind, and also if the wave number is really small, only if you have a few waves. Then those waves, the planetary waves, will move very slowly, or sometimes they'll stop and even retrograde. They may move backwards very slowly. So that's if you have a small wave number, only like 3 or 4 waves. So meteorologists recognize this. The number of waves determines how fast they move. And they call this low index or high index. Low index means that you don't have a lot of waves, only 3 to 4, and you tend to find more meridional flow, and the waves progress very slowly or may even retrograde or move backwards. Whereas high index is when you have a lot of waves. You're looking at 6 or more. Things start moving really fast. The waves are moving fast, especially if you have really strong winds blowing through the waves, and they just move very quickly, and the weather changes also very quickly. So that's a little bit about barotropic instability and how long waves or Rossby waves move. The next PowerPoint presentation and video that we're going to look at is baroclinic instability and how short waves move.